So in this video we're going to look at deriving the equations of motion for an object falling under the force of gravity. But we're only going to do it in one dimension, that is, we're only interested in it dropping down in this y direction. So there won't be any movement in, say, an x direction. So that's a little ball there, that's the earth, and it's dropping down towards the earth, and we want to derive the equations of motion. So in order to derive the equation of motion using the Newtonian method, we could say that the force on this object is equal to the mass times the acceleration. So we could say the force in the y direction is equal to the mass of the object times acceleration. Now we know that the mass of the object is given by the letter m. Now the acceleration we have is actually the acceleration under gravity. So that acceleration has got a value of g, and we have a minus sign here because we've defined the positive axis here as directed up the way, but this is actually falling down the way, so we've got a value of a minus sign here. So we can then write that as mass times, now gravity is an acceleration, so it's the second derivative of position. So if we were to differentiate position once, we get our velocity. If we differentiate it twice, we get our acceleration. So we've got this little equation here then, that minus mg equals my double dot. So what we can do is we'll write our equation here as our my double dot equals minus mg. Now in the x direction here, again we said there won't be any movement in the x direction, but we'll put it in just for completeness here. So we have the mass times acceleration. Well, the acceleration is going to be equal to 0 because there's no movement in the x direction. So these are our two little differential equations that define the motion that we're interested in, and in fact it's only really this one that we're interested in. So now we're going to use the calculus of variations in order to derive these two equations. Now the question that we have is, what is the term that gets minimised? Now this is always the thing that we're looking for at first in the calculus of variations. Now I've put it on quotes here because we don't necessarily know that there's a term going to get minimised. There might be something get maximised, or there might just not be an answer to it. So there could be in effect a point of inflection, in which case there's no a minimum or a maximum. So really we should use the term what value is extremised, or what is the extremum. But in physics we use another term. We would say really what quantity is stationary, and you can see where the word stationary comes from, because when there's an extremum we have a stationary point, and we've seen that in a previous video. So now I actually use the term minimised because there is actually something here that does get minimised. Now the certain something, as we mentioned in a previous video, is called the Lagrangian. Now the Lagrangian is a difference between the kinetic and potential energy. So nature acts in a manner such that it minimises the difference between the kinetic and the potential energy, and you'll sometimes see these terms written out as L for the Lagrangian, T for the kinetic energy, and V for the potential energy. So I've just written them out like this because you will see that in some of the books. So now we know the thing that's going to be minimised is going to be the kinetic energy minus the potential energy. So let's go ahead and we'll work out the kinetic energy, the potential energy, and we'll also look at writing down the Lagrangian. We'll also look at writing down the Euler-Lagrange equation in the next slide. So we're going to write down the Lagrangian, which is the kinetic energy minus the potential energy. So the kinetic energy for our object falling under gravity, well, it's going to be a half mv squared. So the velocity is the rate of change of position, so we can write that in terms of the derivative of position. So we could write it as a half m, and it's going to be the position that's going to be changing is going to be the y position, so it's going to be y dot squared. Now we know there's no any x change, but we'll put it in just for completeness. So there could be a kinetic energy related to the rate of change in the x direction, so we could write that as x dot squared. So this here would be our total kinetic energy. Our potential energy, from the previous videos we've seen potential energy is mass times gravity times height. Well, what's the height in this term? Well, the height is just going to be our height y. And then we can write down our Euler-Lagrange equation. So in this case, our variable we're interested in is our y, which is our height, and it's a change with respect to time. So we can write that as partial L by partial y minus d by t of partial L by partial y dot equals 0. And the function we're interested in is this Lagrangian here. So we're going to have to form this differential equation with this function L. So let's go ahead and we'll do that just now. So we want to differentiate L with respect to y. Now the only term here that's got a term in y in it is this term here. There's no y term here. Okay, now the y dot doesn't count, it's the differential. We're only interested in the actual y term. So all of this here just looks like a constant, okay? So it all just disappears. So whenever you differentiate, all that's left is this here. And our m and our g are just constants. So all you're going to be left with is minus mg. And then we're going to have to differentiate the partial L by partial y dot. And again, whenever we differentiate that with respect to y dot, the only term in y dot is this term here. Everything else looks like a constant. So whenever we differentiate that, we're just going to end up with our my dot, because we're going to have it would be the chain rule for differentiation, so it would be 2 times a half m y dot, and the 2.5 is going to cancel out, so you're just going to be left with the my dot. And then we have to differentiate this my dot with respect to time, so we're just going to get our my double dot. So you end up with this minus mg minus my double dot equals 0, and we could take the minus mg over to the other side, and we've got our my double dot equals minus mg, which is the equation of motion which we derived using the Newtonian mechanics. So that's us derived the same equation using Lagrangian mechanics, or using in effect the calculus of variations. Now we can do the exact same thing with the x component. We can differentiate partial L by partial x, which will give us a value of 0. And then we can differentiate partial L by partial x dot, which will just give us our mx dot. And if we differentiate that again with respect to time, we get our mx double dot, which is going to equal 0. So I suggest you go back, and if you're unsure of any of that, just take your time and read over it. And it's always the thing, when you see these at first, we always look at it and think the differentiation is going to be difficult, but it's actually quite simple differentiation. So that's us finished our little derivation we were interested in doing. I've added this section in here just to cover some of the physics that we'll see in other videos. Now this isn't exhaustive, it's a little introduction. We could potentially cover a whole video series on this subject here alone. Now we mentioned before that nature tends to minimise a certain quantity. Now that quantity is something called the Lagrangian, which is the kinetic energy minus the potential energy. So it's the difference between the kinetic energy and potential energy. So we can say then that if we were to integrate with respect to time from t0 to t1 of this Lagrangian with respect to time, then this is a stationary value, and we call this Hamilton's principle. So really what it's saying is that an object travels in a path such that the Lagrangian is stationary. Now we're interested as well as a simplification to this, and the simplification is that if we were working with a purely conservative force, now in it, for instance, we look at the idea of gravity, and gravity is a conservative force. So what do we mean by a conservative force? So when we go back to the idea of the pendulum swinging, in its original stationary position it's got a maximum potential energy, and when we release it, this potential energy converts to kinetic energy, and over the full swing cycle there's a conversion between kinetic and potential energy. But at any one point in time, if we were to add up the kinetic energy and the potential energy, we would get a constant. Now we're assuming there's no any friction loss at the fulcrum here, and we're imagining it's a perfect system. So we could say then that the kinetic energy plus the potential energy is a constant. So then if we do a little bit of algebra here, we can say that the Lagrangian is the t minus v. So the t plus v as well with above is k. So from these two little equations we can say that v equals k minus t. So we say minus v equals t minus k, and or L equals t plus t minus k. So L equals 2t minus k. Now we'll leave out the k here for a second, and what we can do is we can rewrite this here as I equals 2 times the integral from t0 to t1 of the kinetic energy t with respect to time. Now this is called the principle of least action. So it's really a subset of this Hamilton's principle. So it's really Hamilton's principle employed for conservative forces only. So as I said, we've kind of skimmed over the surface because this is really physics, and the course that we're doing is calculus of variations. But it turns out an awful lot of the calculus of variations did come about via the trying to answer physical questions. So we do learn a little bit of physics as we do it, but we don't need to get into any major detail here in order to just get we really just want to try and get a comprehension or an understanding. But this type of stuff is fascinating in itself, because you could go ahead and start asking questions like how does the object know which path to take? How does it know what the next point is going to give us a minimum value for that Lagrangian? And there's a lot of interesting kind of philosophical questions that this could bring up. So I hope this has been of value to you, and I'll get you on the next video. Goodbye.